Hi, welcome to our talk. How can serverless improve your horticulture? In truth, it's a rather grandiose title for probably something that doesn't quite make it that far. So I'm Clive Hackney. I'm a senior developer with Capgemini. I've been with them for about 11 years now. Spent most of my time writing Java. So the things we did on the hackathon and the things we're about to show you are very different to what I normally do. So that's me.
Yep. And my name is Joao Veiga. I work for Capgemini. I've been with Capgemini for 3 years. And normally in my day job, I just code Java. From my previous background, 15 years ago, I was a C++ programmer. So,
cool. So, what are we here to talk about today? So, has anybody been to the stand yet? There's one nod. We've done well then. So, basically, we're going to talk about what we built and why we built it. We'll do a bit about the tech we're using, a bit of the tech you can't see, so Graal and Pulumi that you can't see. We're going to try and use a board, although you might be able to see what we do with it. And that's really about it. So we're just going to go through our journey down our hackathon. So every year we come to DevOps. We've been coming for 3 or 4 years now. Had various themes over the last few years. For those of you who've been to our stand again, our thing this year is sustainability. So interesting question for the audience. Has anybody ever considered the sustainability of their code? No, me neither. Interesting how we do something that's sustainable, how we make that into a demo, what can we do that actually makes the work we do more sustainable. With lots of things, it's easy. The entire backdrop of our stand is recyclable. That's easy. How do we make sustainable code? How do we do things that are more sustainable? How do we use less power, more efficiency? In fairness, we had 3 days in the woods to do something. We were never going to answer those big questions. So what we've done is we've tried to do something. Let's go to the next slide, actually. So we've come up with an idea where we can maybe show off some of the things we could do, how we could use some data and some things to make things better. So we've got a greenhouse down there. So the idea of the greenhouse was one of our colleagues who hasn't turned up in the room, so that's good. So we can annoy him. He came up with the idea of a greenhouse. So why a greenhouse? Well, it's green, so it's obviously sustainable. But we can do some things with it. We can use some IoT sensors, or we can make some things happen and maybe make the growing process more efficient. And then from the compute side, if we use lambdas, if we use AWS or Google or Azure or any other cloud provider, of which there are several downstairs, we can make better use of the compute power that we use. So we can become more efficient. So with that in mind, we set about building a demo. So what were the things in the greenhouse we could control? We can control the lights. We can turn lights on and off. We can have a light sensor, so when it goes dark, the lights come on. When it gets bright, the lights go off. Humidity, plants don't like it when it's too moist, or some don't, some do. We can control that slightly. So there's a fan down there, so if it gets too humid in there, the fan turns on, blows the humid air out. Temperature's fairly obvious. Temperature's the cool one. If you haven't done the temperature one, I recommend it. Just because anybody who likes seeing a window open by itself is just, I find that satisfying. I don't know, it might be just me, I'm weird. It's quite nice. And moisture is the same thing. So those are the 4 things we've set about trying to control. We had some other ideas as well, but never made it off the ground, in fairness.
Yep.
So that's where we are. So what did we do? So that was the view from our hackathon house out the front door. Every year we try and go somewhere to do a hackathon. Lots of reasons for doing it. It's a great way to meet our colleagues. I've never met Joao till I went on the hackathon.
Pretty much.
Yeah, we met about once, twice.
We met before, but
yeah. All right. But it's not a stand-up show or something.
Yes.
So, but we haven't met very often. Let's put it that way. So it's a great way to meet our colleagues. We're a company. As a company, we're distributed. So he's London-based. I live in Manchester. I work in Bristol. Go work that one out. So we get a few days away to go and learn some interesting stuff. As we said at the start, the stuff we've done on the hackathon isn't the stuff we do on our day jobs. It might be soon. We might get a project where we do this stuff. But at the moment, it's the first time I'd certainly had to go at IoT, and it's certainly the first time we've done some of the serverless stuff we did. And in truth, let's be honest, going to the middle of the Peak District for 3 days, not having to worry about work. There was a hot tub. Nobody used it this time. Last time we did. It's just nice. So why not? So that's the venue. We've done the ideas. So now we needed to do something to do with... So we had to go and do a shopping list. So here's all the things we bought. So all of these things should now, or most of them, are running inside our greenhouse. And so you'll see over there lies all the ESP boards, which Joao will talk about in a minute. You'll notice there's 37 sensors in there. There's not 37 sensors in our greenhouse. We didn't use them all. I think there's one in there we actually wanted. That was the cheapest way to buy them. And let's face it, it's not every day you're going to spend 400 quid of your company's money on toys. So why not? I'm now going to hand over to Joao. He's going to talk you through some of the ESP stuff.
Right. So when we took the decision to implement an automated greenhouse, we had to make some decisions about how we're going to control it. So the initial step is that we had to select something to capture and to act upon the environment. So I don't know if you guys are familiar with the embedded devices, tiny microcontrollers like Arduino. Has anyone ever done the blinking LED? Yes, good. So we end up by choosing the ESP32 because it's a bit more powerful than the Arduino itself, and it contains one thing which is pretty important. It's all embedded, and it contains both Wi-Fi and Bluetooth. So the Bluetooth spec goes up to 4.2, which is pretty impressive. And price-wise, it's actually not that different from the Arduino itself. And from an entry point perspective, in terms of programming, you can actually program this device as if you were programming an Arduino. There is actually just a tiny set of differences. Or you can run this properly in its own real-time operating system. So in essence, you actually do get to use the full dual cores. It runs up to 240 megahertz, which is pretty good. And it has a real impressive ultra-low power core. So this thing, if you for sensor applications where you're actually going to collect, for example, the room temperature, and you put the device into a hibernation, if you program it through the ESP IDF, you get to use these low power cores, and it actually can get it into deep sleep. When it's into deep sleep, it consumes like microamps. It's very, very impressive. And on top of that, this device itself, it's sort of they were smart in a way. So they also hooked up into the way that you can actually program it with the Arduino. So for those of you who are interested about these devices and you haven't had a chance, so Arduino is going to be the lowest entry point that you can get in terms of getting yourself to actually run something on such a device. So also what the Arduino guys did was, which is also pretty smart, is that at the time when they launched it, there wasn't a lot of people that knew how to program this, and they didn't really necessarily know how to program the C code. So they created their own embedded environment based on the processing, and they actually allow people to share the code. So I'm going to show you a small variation on how to program these devices. and using a slightly different platform. So I'm not going to use the Arduino IDE, which you could. By the way, the device that we were talking about is this little one, so you can see it inside, in its actual size. So in reality, what you have here, it's a dev board. And this dev board is relatively inexpensive. In the old days, if you wanted to buy a dev board from a manufacturer, you would end up by paying like 400, 500 pounds. This costs something like 12 pounds, which is almost nothing. So the actual chip itself, it's only this and this tiny little section at the top. What you've got as well over here is some additional modules like an OLED and some battery management and charging. So it's very, very small. And you can even go even smaller with some of its little brother. So that's not the one. So the question now is, how do you program these devices? So specifically, I want to talk to you about something called Platform I/O. So I don't know is anyone here familiar with the Platform I/O? Yeah? Good. So what Platform I/O allows you to do is to do something on top of what the Arduino IDE doesn't necessarily do in this manner, which is to actually add your dependencies to your code. So in essence, you can search for other people's libraries, and you can, in essence, just hook them up to your code. So what we did is that most of the modules, so we have this modularized way of building the application, where we have the real code that's actually, this one is the spray gun thingy, where's the code, you can see it over here, and then we just wire all the other stuff through the dependencies. So pretty much this allows us to actually just create the modules that allow us to do the Wi-Fi access, security, AWS gateway, and putting also the AWS dependencies, and just to have to deal with the actual code of executing a command or sending things. So one of the unique selling points, you get something similar in the Arduino IDE. If you go to the onto this, is that you can search for anyone's library. So if they published it, you can actually search for it and use it. Let's say UAG. So this is a very common library that it's used for controlling the OLED screens, the LCEs. And if you can click on it, in general terms, people are going to tell you, for example, they're going to add some code that you can actually just refer to, so that you don't have to program this blindly. So this is important if you are starting up. And then I'm going to show you a completely different code, which is going to have it on the Platform I/O. So this is what it does. The libdeps, it's standard, just npm thingy, but applied to these devices. And by the way, you can also, if you are more into Node, you can actually program this in Node. So there is a tiny kernel that you can deploy to these devices, and you can program it in Node. So I'm just going to show you a simple, just for completeness purposes. So I'll just show you a very simple application, and what's the workflow. It's not really that complicated. So what I did here is it's based on there seems to be a resurgence on the retro computers and things like that. So what I did is just to recreate a sprite, which it's here. So all of this stuff. So I just decided to recreate what's a sprite that you have in the old computers with a spectrum, and just do it the same way for this library. So what this is going to do is going to print one of the characters from the Space Invaders, and it's just going to shift it around the window. There's one little thing. You'll have to trust me that the character actually also flaps its hands, but you won't be able to see it because this is way too tiny. But I'll just show you roughly how does it look like, and what's the code experience compiling this. So if I just connect this, actually it's already loaded. So, but what I'm going to do is to recompile this again. So You can also use Platform I/O on Atom if you want to. And the buttons are a little bit bigger, but I tend to have some difficulties to find exactly what I need over here. So what we did in this particular point is just to do a build, and now we're actually going to upload. And when we do upload, it's going to upload this to the device. So still going, and I add a tiny little thing just to do a so if I now hit the reset, ta-da! So it did execute the code. So here they are. It's a couple of characters, and I think I was doing some tests, attempting to test what's the maximum FPS that you can get on one of these devices. I don't recall exactly what was the value, and that's pretty much it on this. So this covers the bit about the programming, and so what we decided and what we did at the hackathon is that we were actually able to program all the sensors and actuators, and we just wire them up in a pair configuration. So to have temperature to actuate the window, as Clive mentioned, and pretty much we had that bit done in 3 days. Right?
Yeah.
So Clive will talk you more about the hackathon itself.
So we've now got a bunch of sensors running off ESP2 boards. Got a bunch of actuators. The question is, how do they talk to each other? How do we actually get the window to open when it gets hot? So the big question mark in the middle is what do we do next? How do we wire these things up? And in truth, this is where it gets a bit more interesting. There's lots of options. We considered running a Raspberry Pi inside the greenhouse. Just let everything talk to a Raspberry Pi. It's completely offline. It's not very cloudy though, and not very cool. Turns out there's lots of AWS, there's lots of IoT solutions out there. Google have one. You might have guessed already because I just said AWS. So we decided to use AWS's one. So in the middle of that, we plonked AWS IoT, IoT Core. There's about 7 or 8 other things you can do with the IoT Core afterwards, none of which we had time to look at. So hopefully, if the gods of network are being kind, which browser is in, Joe?
That's the one.
No, it's there, sorry. No.
It is. It's
Yeah, I want that tab.
Click on that one.
Yeah, there we go. Right, so AWS. So a quick tour of IoT Core. So you can tell from the picture when we turned the demo back on, it's about half a day ago, is when the thing started to connect to it again. So the devices themselves are connecting via MQTT. So IoT Core is running an MQTT broker in the background for us. And on that, it's got a set of topics. And we'll go through quickly how the topics are exposed and how we connect to it. Basically, it's all TLS, it's all secured. So every one of those devices you see in the greenhouse has got a private and public key on it. I'm going to get this the wrong way around now. There's a certificate in AWS, and it's authenticating those, and it's also doing a check to make sure that the device is allowed to see it. So there's a policy applied. So we'll go through it quickly. If you want to onboard something really quickly, it's actually really trivial. I won't do this now, but you can configure a device, and these will run Python, Node.js, Java, and up various other things out of the box. You download the kit, and it comes with all the stuff you need. It's really quite easy. Unfortunately, it didn't work so well on the boards because the boards were all written in C. So we had to do a bit of extra work to get those to work. But it wasn't overly difficult. It wasn't terrible. There's also AWS RTOS and an embedded system you can use. So you can use a kit that they've got that you can build onto the boards. We investigated it, but in truth, the amount of time we had to do the demo, it became overly difficult. I'm sure when you've got it all working, it's brilliant, but we didn't get a chance to get it working properly. So, Core has this concept of a thing called things. So everything is a device, but we didn't do it quite like that, mainly because it was the first time doing it. So we created the greenhouse as a thing. So within the greenhouse, there's actually AWS wants 4 things because it wants to manage them all differently. And you can do some things to do with shadows and letting them work offline. So if the connection drops and things like that, you can actually have a shadow. You talk to the shadow, and then it's updated when the device comes back online. Because of the way we've configured it, we can't actually do that because it's either all or nothing. So that the greenhouse is online, the greenhouse isn't online. In retrospect, we'd have done something a bit different. So within DevOps Greenhouse, we define these are certificates, and here's the policy that we're talking about. So for those of you who know AWS, I'm sure this makes perfect sense to you. For an AWS Policy virgin, I was quite confused by all this. And this, interestingly, is the only place we define the topics. So we don't define the MQTT topics anywhere else, we just define them in the policy. It appears that Core allows you to basically call anything, and it's a policy that restricts access and basically defines it. So we allow certain things to publish and receive, and down the bottom we've got a set of resources that are allowed to talk to it. So that's all good. So in our code for our IoT containers, they've all got an ID that says greenhouse star dash light, humidity, whatever else it is. So that's the basic authentication. So they're talking to MQTT broker. That's publishing things. We didn't do anything with secure and defend. The interesting thing and the thing that makes it do stuff is this thing called rules. As the name kind of suggests, it's what you want to happen when something arrives on your broker. So if I look at the right light one, so this top bit is obviously a SQL-like syntax. So that's basically saying everything that arrives on the topic measurement light, pass it to these rules that you defined below. I don't quite know why it decides it's rules and then calls them actions, but it's a thing. You can also there's a where clause on it. So if you're pulling JSON, which we are, you're pulling JSON off the topic, you can say where certain field equals X or certain field equals Y, and you can do some filtering so you can have different queries for the same topic based on your package that comes in. What we do with all of on our first pass at the end of the hackathon, we were writing everything. So everything that came in from measurements was written out to a Dynamo table. Again, it's dead simple to configure. All this stuff can be scripted as well. So we've scripted some of it, and Joao will show you how you script some of it with Pulumi later. But in our first bash, we obviously went to the nice big AWS console and did it manually. This takes every measurement, creates a partition timestamp. So timestamp is a variable in the payload that came in. So there's a base payload that says timestamp. It's using that as the partition key in DynamoDB. We've got a sort ID, a sensor ID. We send it to CloudWatch. So we've created some custom metrics. So the light value. So we log all of everything that comes through a topic gets logged out. So all the measurements get logged out and all the commands that go back get logged out. We can send it to a lambda function. That one doesn't exist anymore because we deleted it. So some of the other ones that we'll show later are there. And we also tried to play around with Elasticsearch, which has a few interesting quirks, but all this data is actually in Elasticsearch as well. So you pump it straight out to there. And of course, there's a whole other list of things you can do, which I won't take you through. But those are the ones we use. So for all of our stuff, we are logging it out to CloudWatch. So if I go to CloudWatch, if I go to our dashboard, greenhouse metrics, hopefully we should see, he says hopefully, if it's actually running at the moment. So there's the current values. You can tell when people started to play around with things and move things around because the graph drops dramatically. So somebody's pulled out the moisture sensor there and dropped it in the dry patch. So that's just logging it over time. Interesting, slightly quirky thing with the commands is because there's not many commands going through, and CloudWatch only shows you averages. Eventually they drop to 0. Yeah. So there's been no commands to open the window, mainly because everybody's in a conference now and not down by the greenhouse doing things. And very still, and the moisture is obviously 0 because it's in the dry one. I
think the moisture could be dead from that.
The moisture's dead. The big question is how long the actuator on the window lasts. I think is the question for the. We'll see how long that lasts.
Yeah.
So that's just writing it out to CloudWatch. So if I go back to IoT Core, the last thing we can do within IoT Core is we can test that our things are set up properly. So if I stick in here, so if I subscribe to measurements, light's a good one. I subscribe to that topic. If I do the same for command, let's publish to a topic, subscribe to a topic. Hopefully, they get a little green dot next to them after a while, and that means we can actually see the messages going through. So here's an event. So this is event coming out of the light meter, and it says it's currently 91% light. I don't know what that. Yeah.
It's a relative value.
It's
I mean, the sensor that we're using is resistive, so it doesn't. It's not incredibly accurate. So.
And we can see the command for the lights going back. So all we do for the lights is we take the 100%, the number we get back off 100 and send it back. So the testing thing's quite good, and that's IoT Core in a nutshell. So if I go if I go back to the presentation. So now we find ourselves in this situation. So we've got our sensors, actuators, and they're wired up using IoT Gateway. We wrote some basic lambda functions originally to just fire the things backwards and forwards. We're writing stuff out to metrics and we're writing stuff out to DynamoDB. But we wanted to take it further.
Yeah. So as you can see, so when we ended up the hackathon, we had the sensors and actuators working, and we had in a way a bit of a primitive infrastructure on AWS. But we wanted to expand a bit on the concept. This was specific to the actual control of these actuators. So originally, before we even started the hackathon, we attempted to do this in a distributed manner. So the sensors and the actuators would be able to act upon themselves. So we attempted to do this, and we were going to use a protocol which is relatively new. So it's the mesh networks for Bluetooth low energy. So this is it's relatively new, something like 2 years has been launched, or maybe 1 year. But the implementations are quite new. So we attempted to get those to run and to control themselves. But we found that there wasn't. We was actually just playing with development APIs, and with an API which was actually not yet that mature. So we dropped that. So we needed to control this. So we started off with the IoT Core. Let's say that there is a set of cloud instances which are going to dictate what should be the behavior. So the sensor reports what's the actual measurement, and then something on the cloud is going to receive that and then act upon it. So what we've done at the hackathon covers this bit here and up to the IoT Core. Additionally with a couple of shunts with lambdas and all of that. But what we wanted to have is to have a type of microservices architecture based on domain-driven design rules, where we would actually have a set of microservices to represent different things. Like, for example, the greenhouse itself, but it also could represent things like the plant. So we have over there a couple of ones, like plant 1, plant 2, plant 3. And you can imagine that could be something that's a specialized microservice that is going to control what should be the behavior of a plant inside the greenhouse. So what you end up is with this sort of architecture, which is some of the important parts. It's the event store that pretty much just, it's over here, captures everything that's happening on the system. So Clive just mentioned to you about the rules in the IoT core, which actually published to queues. So everything ends up in a DynamoDB table, and from that, every single let's call it microservice, because this is a very loose term. What we're doing is a pure cloud native architecture. So your deployment boundary it's not a Spring Boot application. You're going to deploy lambdas and databases to maintain the internal state, and at best you have tags that allow you to actually tell you what should be the components of a particular microservice. So we wanted to do this a little bit more at scale, and also add some APIs so that we could actually query the state of the system. So yeah, so we want to do all of this, but this actually is very difficult to do if you're going to hand crank those. And as we mentioned, I mean, we're doing this in a out of hours, so it's complex and difficult if you have to do all of this manually. So we had to settle for something. So we needed a tool that would allow us to build this the infrastructure on the AWS. So could have gone for CloudFormation, which is AWS's native tool. Could have gone for Terraform. But I think in a way the hackathons are a really good way for you just to try out new things. So a colleague of ours suggested that we use Pulumi. So what Pulumi is it's actually a wrapper around, it does wrap around Terraform for most of the providers. You can actually build your infrastructure as code, and it uses this programming model that you already know. So you can program in JavaScript, TypeScript. You can do it go with Go or Python. So the advantage of this is that there is a much lower barrier of entry for you to actually start doing your infrastructure, because probably you're going to be familiar with one of these languages. And if you're not, you could at least go for TypeScript, because it shares quite a lot of the similarities with Java. And what it does over and above the Terraform is that it manages the state for you. So when you create your stack, as your application gets compiled, it's going to maintain that state as you publish your infrastructure. I'm going to show you a hands-on. I actually grabbed one of the examples from Pulumi, and just wanted to show as a very simple example of an application that you can actually deploy. The interesting part about this is that there is specifically if you're going to program, if your favorite language is Node.js, there is the lines between what's your infrastructure code and what's your actual application code, they are quite blurred. So let's check this. So that's not the one. Demo Pulumi Gateway. That's the one. Right. So what we have over here is a simple application for Pulumi, and what this is going to do is to create an API on AWS, a REST API, which is then going to. It's actually very difficult for you to see this. I don't think I can control it at all. But what it does is that it creates a couple of resources. So the first one is going to do is going to be a DynamoDB table, and then it's going to do this API. So the API is going to then have this event handler. So every time that you invoke it, what it does is going to go through the client, is going to get the current state of that particular route, and then increment it and store it in the same table, on the same table. So it's like get, increment, and save. So on the web. So the way that you interact with this now is that, let me see if I can make this as big as I can. So And that means that. Better. So the way that you that script, when you issue Pulumi app, is going to process that that index file, and it's going to tell you what it's going to do, and it's going to create a plan. So a couple of interesting things is that it does provide you, Pulumi does provide you some high-level APIs that allow you to create complex things. So see, we went on with a package that said this special X API, and then it creates roles, it creates a function, the REST API, and all of that. So those are the physical things that you need to create in AWS to do this. So as a starting point, that's fair enough. But if, as you actually progress and start to learn more about the tooling, you actually need to understand what those are over there, because that's the AWS specific language. And then what this does is that you notice that, for example, the table was defined at the top, but this is going to understand what's going to be dependencies. So this is actually a very complicated thing, what happens in the background, because some of the resources that you're hooking up, you don't know what they are before they are created. And this is actually dealing with all of that. So normally you would go, I create the table. Now that I know that what the table is, I'm going to hook it up to a function through a mapper. So there is this notion of what's going to be created ahead. So and Pulumi is going to take care of that. So now what we can do, so there was a little thing that we did over here that actually could have done this a little bit bigger. So there is this exports on the endpoint that's going to give the URL. So if you hit this straight away, it can actually give you what's the current counter value. And so if we do this, then do devox. At this moment in time on AWS is initializing everything. So the API was already listening, but the Lambda function wasn't. So this is pretty much what you get from it. So it's a counter. And if you execute it again, you get a 2. And it can also deal with really complex scenarios that, for example, probably they're a little bit more difficult in Terraform. So if some of your colleagues were to actually delete part of your stack, this would do through the refresh mechanism would actually be able to understand what's the current state on the AWS front, merge that state, and then when you do the update, would actually update with everything that needs to be done, and would actually get this to resolve itself. So I was planning to actually delete this, but delete one of the resources on AWS, but I think it's a lot. I mentioned the case that it actually can deal with that. So it's if you're interested about this in particular, we will have a couple of sessions in the Coding Cafe where we can actually show you more about it. So. But in essence, there's something that's a bit strange. So in the code that I showed you, there is a script that creates your AWS infrastructure, but it also contained the code that which was written in Node.js, and that code was specifically there. So it's actually very difficult if you're going to do that. It's your testing is going to be difficult to be done. So it's much better to externalize things. So what you've got over there in the event handlers, you definitely want to take that all away, get it onto another class and onto a project that you actually do all your testing and do it from there. So in essence, you just define that as a zip file or a package that gets packaged another project, and your infrastructure just refers to that. It's smart enough to understand, for example, when you haven't changed anything in your code and your package is still the same, it doesn't need to deploy that. And also, probably, well, I guess it's the tone of this conference, we would like to change that into Java. And that's pretty much what we're going to do. So moving on to Java itself, it's actually not that complicated. In general terms, the AWS has been supporting Java for a while. So you can write your lambdas in Java. So we went on with this very simple strategy where we just created what sometimes is called the fat jar. So you have all your code. You just wrap up all the dependencies, and pretty much you just create one gigantic jar. So that's pretty much what we did. So as a starting point, so we didn't grab anything off the web or anything like that, but it's just the dependencies. So we took the AWS SDK. So package it all up in a single jar with Maven, execute that, and then we get that the package is too big. So I couldn't actually deploy this straight away because we're getting a jar file which was something like, I think it exceeded the limit just by a tiny bit, but it was 33 megs. In general terms, we were looking at so when comparing, for example, with Node.js, we're just talking about a couple of kilobytes. So, right, so digging up, doing some reading and all of that. So we initially anticipated that from we actually depended on the AWS SDK. So we just pruned all the dependencies, just depending on DynamoDB and the lambdas, and then we get an execution timeout. So carrying out with that, so we originally had 5 seconds. We know that Java is not necessarily the fastest when it comes to actually startup time. And what we did is just increase to 20 seconds. We're still getting an execution timeout. It's simply not starting. So the execution timeout doesn't actually tell you what's the underlying error. So we definitely need to see that. So we just increased from 20 to 60 seconds. So this means that we'll give this Lambda function 60 seconds to execute. And then we could see it out of memory. So in this bit, so we're dealing with the code. So we did a sort of like for like. We didn't have anything fancy on that, just the AWS dependency which would actually pick up an event and save it onto a projection. Nothing very complex. So we got the out of memory. Specifically, we're getting errors on the meta space. So it is already telling you that there's not even enough memory just to load things, and specifically on the application code, not even the runtime one. So we just increased the memory to 192 megabytes as a starting point, and then our lambda was executed. But it took 15 seconds to initialize. So what we were seeing before is that if we just allowed the Java Lambda to have the minimum amount of memory that we could give it, it would actually take a long time to initialize. If we went on to 256 megabytes, then it would actually initialize much faster, but never at the rate that we would compare it with, for example, with Node.js. So at this moment in time, this is just the pure initialization. So the Lambda is going to be deployed onto your AWS, and the first time that it's invoked, AWS is going to perform the action that will trigger the bootstrapping. So the Lambda starts in a way. So it's then it's going to initialize all the code, and it's going to be ready to process more requests. So the first time there is a significant amount of things that need to happen for your Java application to run. And what happens is that the subsequent invocation is going to be much faster. So what that means is that if you arrange a way that you can actually just poke your Lambda so that it never actually gets taken out from the memory from AWS, or you just actually constantly just doing a sort of a ping every, I don't know, I think the value is around 40 minutes, then you could still maintain it in the state that it's running. But you could consider something else, Graal. So there's been other attempts. So Graal, I don't know how many people here are familiar with Graal. Hopefully a lot. Yes. Okay. So Graal, that's pretty surprising. So Graal is a native. It's a tool which allows you to compile Java to a native package. So in essence, what you end up is not the compile once and run everywhere model. So you're actually going to compile it specific to a target architecture. So if I compile it on my Mac, it's not going to run on Linux at all. So what this allows you to do is then it's going to apply this ahead of time compilation. So essentially, your application is going to be quite fast on the startups. So yeah, so that's well, I told you before that I was from a C++ background, so I kind of like some of the speed, but I also like a lot of the things that Java allows you to do. There's one thing is that that I specifically mentioned over there is about the third-party libraries, and this is important. Is that the process to actually get on this running to Graal, it's slightly different. So I told you what was the process for Java. So and fixing up just the simple running a Java lambda took at best like an hour or so. But fixing up to run it with Graal and figuring out what was wrong, it actually took days. It's very, very different. So the strategy for this is that we're going to compile a native package that we're going to deploy onto AWS. So AWS does have support for native lambdas. That means that you are responsible for all the bootstrapping and communicating and instantiating a lambda. So the strategy for this is like fix it until it compiles. So Jackson, which is a common, well, a JSON library, started to act up a bit, which wasn't really unexpected, as I've written. But then, so what we needed to do, so the problem is that the libraries that require a lot of proxying and do a lot of reflection, they are going to struggle with Graal, because ahead of time compilation, it's not going to be very friendly towards things that need to run based on the execution. So if you have some execution code that's going to run a class which is either car or truck, but you can only tell it at runtime, what Graal is going to do during the compilation is going to start stripping out stuff. So this is really weird, because now you just it reports it can't find the default constructor, and you know that the JRE is going to place that for you, but it's been stripped away. So there is an important lesson on this, is that the code that you think that you're running is probably not the code that you're running on Graal, because your jar that you originally compiled and unit tested and all of that is actually being gone through something that's going to analyze it, find dependencies, find what it thinks to be that code. And if you have, for example, Jackson mix-ins, which was one of the issues that we have for serializers, then you actually start having problems, because Graal will just take those away. And when it gets to running your code, you're actually not seeing it behaving properly. So this is pretty much it. So the strategy, so starting off with fixing until it compiles, add reflection, then define resources, then more resources. I even had to add what's it called, wildcards to allow for JSON files which were dependent on that were provided with the original third-party library to be included into the package. Otherwise, they wouldn't. But then it did execute. And it did actually start up at the same speed. So I don't have, well, it's actually running a bit out of time. But on top of that, I don't actually have the values to provide to you as a comparison, because in essence this was not an extensive comparison, and it would be unfair in a way to start throwing attempting to show that this was a detailed comparison. So no optimizations were done nor anything like that. But in reality, we actually got the Lambda to execute at least faster than the Node.js. So it did initialize just like 100 milliseconds slower at 2.2 seconds, but then when it was running, it was way faster. And I think we're actually, so we had originally planned to do a bit of a native tour. So in essence, we would actually show you the resources that we've created. But in essence, I mean, this is this is not the right scenario. And given that we're going to have a coding cafe where we're actually going to demonstrate some of these things, you can actually interact with these. You can come and join it tomorrow, and we can definitely demonstrate this to you. So I'll hand over to Clive.
I think that's us pretty much out of time,
well,
isn't it?
Yes.
So it's a bit of our journey to get to that greenhouse there. It's been interesting. We use lots of interesting tech, and it's clearly I'm keeping people from their lunch now. So if anybody's got any questions, come and see us afterwards. It's fine. But that's a lot. Thanks very much for your time.